Let us start. See, the whole talk will be like, as I said, it will be an overview of the Einstein gravity, and I'll be discussing some basic ideas of cosmology and astrophysics. To start with, uh, can you tell me what is cosmology? It is a very fundamental question that everyone should start with before actually knowing the topic and studying its basic things. So, actually, cosmology is a scientific study of the origin, evolution, structure, and eventual fate of the universe. Right? So, what the nature of time comes, those and they know the concept of space, right? X axis, Y axis, Z axis, we all know. But from this revolutionary idea of space and time comes the Einstein's general theory of relativity. So, cosmology enables us to understand the nature of the space time and the universe or the cosmos as a whole. Now, you can see genre, namely the physics, astronomy, and mathematics. And how it has evolved over the time. This from the very early stage to the present stage. How it has evolved time, the scientific study is called the cosmology. Some key topics include, first of all, the Big Bang theory. Actually, this theory tells that universe originated from a Big Bang singularity, right? So that is why the name is a Big Bang theory. And according to this theory, the universe began from a Big Bang singularity, the leading explanation for the universe, origin of the universe. Next comes the dark matter and dark energy. These are some very mysterious substances that actually influence the universe. I will come to this topic a little later in the course of my talk. Next, you see microwave background radiation. So CMBR, observational topic in cosmology that actually proves a lot of cosmological phenomena. So the after or the early universe, I'll show you in a pictorial form about the cosmic evolution, the time frame, everything, the stages of the evolution in the next slide. Next comes the structures were formed during the evolution, and ultimately the fate of the universe. That means what will happen to the universe in the future, whether it will forever expand or it will collapse. So this is the eventual fate of the universe. So starting from the very origin of the universe, its stages of evolution, and finally the present era of evolution and what will happen in the future, the whole scientific study is all about the term cosmology. Now, pictorial universe, Big Bang singularity. Next comes the inflation, also a very leading area of research in cosmology, namely the inflationary cosmology. Okay, so many research in modified gravity theories as well as in Einstein gravity. Okay, so next comes, as I said, the afterglow light, and this is the years in light years. Next comes the dark ages. Then you can see that planets, etc. The universe starts illuminating with all these formations of the large scale structures. And there comes the present era of accelerated expansion. As you can see, this represents the present era of accelerated expansion, and observations are in the favor that universe is expanding at what is referred as the Big Bang expansion, and you can see the time, right? This figure, as a whole, early stages of cosmic evolution. Just I'll give some brief ideas. If anybody is interested to learn in detail, they can study books. I'll refer which books you need to follow. So let us start with the quantum fluctuations. As I showed, the very early phase is the quantum fluctuations, right? So actually, at small scale, what happens? Produces some fluctuations in the energy density. Okay, so these fluctuations were present in the primordial universe. The universe that that the Big Bang explosion was there, universe formed, and that stage is known as the primordial universe. And regarding the quantum fluctuations, what happened? These fluctuations were present in the primordial universe and cosmic evolution that comes after that. And these quantum fluctuations serve as the seeds for large scale structure formation like the galaxies, clusters, and superclusters. Next, you can see it's a very the universe experience characterize the expansion of the universe by cosmic scale factor. In cosmology, in Friedman cosmology, we get the idea of cosmic scale factor and Hubble parameter. Then you will see T, which is the cosmic scale factor that is exponential in nature. That means evolutionary era had, you can see that the universe grew by that size in just this small period of time. So this era is the inflation. And inflation smooths out the universe, partial uniformity. Next comes light pattern. Here, what happened? Universe combined at that time. So you can get a lot of images of this kind of cosmic microwave background. It's a snapshot from NASA or ESA archives. You can refer, you can Google, and you can see the images. Next comes the dark ages. Actually, these ages started few hundred millions after the Big Bang occurred. So actually, what happened is that after the cosmic microwave background is released, now the universe contains mostly neutral hydrogen, and with a from inflation grow under gravity, and this led to the formation of the first stars and galaxies. The first stars, as you can see, just after the dark ages, the development of the galaxies, and here, as you can see, the first stars about 400 million years. The first stars about 400 million years, I said. Next is the really happened due to the clumping of matter due to gravity, leading to the formation of the large scale structures like stars, planets over billions of years. Next is the final thing that I will be talking about is the present era of accelerated expansion. Now, many observations are in favor that at present, universe is experiencing an accelerated expansion, what we say as the late time acceleration. Okay, so actually, this uh, behind this accelerated expansion of the universe, and that mysterious energy is the dark energy. Okay, so that the dark energy actually is responsible for this kind of accelerated expansion of the universe at present. So you can see the time it's started 5 billion years ago till present. So these are various cosmic like stages of evolution. Now, what is modern cosmology? In order to learn about modern the cosmological principle, when the great Albert Einstein's theory of general relativity. So these are the three ingredients of cosmology. So what is cosmological principle? States that universe on the large scale, say of the scale 10 to the power 8 to 10 to the power 9 light years, universe appears to be homogeneous and isotropic at the outset. Okay, so that means what is the essence? Whatever in whichever direction you just look at the universe, you will look the same. That means there are no preferential points or preferential directions. That is what the cosmological principle tells us, that universe looks homogeneous and isotropic. And the biggest observational support is cosmic microwave background radiation. Okay. Next comes the Wells postulate. Now, if I there, there should be some postulate that can tell us what are the possible matter content present in the universe. Wells postulate guarantees the matter content of the universe, which it is known as perfect fluid. Okay, so the second ingredient of modern cosmology, the Wells postulate, it states that the matter content of the fluid cosmological model, if we take into account, that should be a perfect fluid. Now, what is the definition of a perfect fluid? The perfect fluid should obey the energy momentum, should have the expression for energy momentum tensor like this. Again, those who do not answers for them, I'm going to speak a lot of things in the coming slides, but just for the time being, you just agree to this point that yes, perfect fluid or some kind of fluid physical models, the matter content that will have expression for energy momentum tensor like this. Okay, next, uh, final ingredient, and it's the most important ingredient of modern cosmology, which is the general theory of relativity. So why this theory is so much popular? What is there in this theory? Many people, they are very afraid of thinking about that Einstein's theory, so we won't be able to understand. So the same thing happened to me also when I was in my BSc days. However, this theory is really, really very fascinating, and it depicts the most beautiful relation between uh, physical quantity, that is matter, and geometry of space-time. So can we imagine that this revolutionary idea was given by Albert Einstein? Only Einstein can do so, giving a relation between a physical quantity, matter of something, and to its signatures. That means it is making an interplay between matter and geometry. Only Einstein could do so, right? So there lies the importance and beauty of his Einstein's field equations. Now let us move our focus from the cosmology to Einstein gravity, as the title of my talk suggests. The revolutionary idea given by Einstein was this: gravity as curvature of space-time. Now, what did Newton? Gravity like a force that acts between two objects at a distance, right? But in Einstein gravity, gravity has been looked upon from a very, very different angle, which is the curvature of space-time. Now, how you can understand this untrivial statement? That seems it's very untrivial, possible. But if you look at, you will be able to understand. So if there is a space-time manifold like this, and if you put a massive object, it will undergo some depression. You can see that. Why does this happen? Because of the mass or the energy. So Einstein pointed this. He said that mass and energy actually carve the space-time manifold. So if you consider the four-dimensional space-time manifold where x, y, z, three space coordinate axis, and the fourth one being the time coordinate, then that is a four-dimensional manifold. That is why, in order to learn general relativity, if you want to learn that properly, you should have some idea of the manifold theory of differential geometry and the tensors. Okay, so it is think of, and if you just see object, it will have the curvature of the space-time. So actually, he proposed that mass and energy curve space-time, and this curvature will dictate how object will move from one point to the another in the space-time manifold. For example, take sun. Sun creates a dent in the space-time, and other objects like the planets will follow some curved paths around the sun. And this carved path in the language of general relativity or differential geometry are what is referred as geodesic. Okay. Now you can easily understand the difference between Newtonian theory and Einstein gravity. In Newtonian theory, the gravity is nothing but a force, right? And the space and time are indistinguishable. That means time was absolute over there. But here, space and time are different identities in Einstein gravity. And the most important thing is that um, the gravity, is responsible for the curvature of the space-time. Now, keeping this thing in mind, he wrote his set of equations, what is popularly referred as Einstein's field equations. So, the core of general relativity is this set of equations that actually describe how mass and energy determine the space time curvature. Now, why did I say that Einstein's field equations showcases a beautiful interplay between matter and geometry? You can see that this part is representative of the geometry and this part is representative of the matter. Okay, so here G mu nu, which is occurring on the left hand side, it represents the space-time curvature. That means what I said as geometry of space-time. And T mu nu, the energy momentum tensor, which is related to the matter and energy distribution that is occurring on the right hand side, as you can see. Lambda is the cosmological constant. Actually, this is linked with the dark energy that I was talking about a few slides back. Capital G is Newton's gravitational constant and c being the speed of light. Okay, so this revolutionary Einstein's field equation is actually the core of general relativity. Some key inventions of special theory of relativity. As I said, special theory of relativity was also proposed by the famous Albert Einstein, where this equation E equal to mc square, all of you know, I think, it states that mass and energy are interchangeable. And what are the key takeaways of general theory of relativity? Einstein's general theory of relativity gives us the insights of gravity waves, very, very important and current area of research in the field. Gravitational waves or gravity waves, or many people say gravity wave astronomy. Next comes gravitational lensing effects in astronomy. This is also a very, very important part because gravitational lensing effects in astronomy are very, very related to black hole physics, wormhole physics, etc. These are all some takeaways of general theory of relativity. Next comes black teaching. This I will talk about in case of shadows of black hole and wormholes in my upcoming slides. This was captured by Event Horizon Telescope. So these are some observations that guarantee that yes, Einstein's general theory of relativity is the most well accepted theory of gravity till date. And finally, the expanding universe and cosmology. So every stage of cosmic evolution can be described using the Einstein's field equations. Now, for those who are interested, if you want to learn the geometry behind Einstein gravity, let me tell you, you should have some idea of the Lorentzian geometry. Now, what is this? Actually, in differential geometry, there is a terminology, namely pseudo-Riemannian geometry. And there are two principal classifications of pseudo-Riemannian geometry. One is the Riemannian geometry, and the other is the Lorentzian geometry. This Lorentzian geometry is very interesting in the sense that idea of causality, that means past, future, since time is involved. So with respect to the present epoch or time, I can describe my future, I can describe some events in the past. So this beautiful idea of causal vectors, or rather causality, is found in Lorentzian geometry, which is absent in Riemannian geometry. So for beginners who want to learn the geometric aspects of general relativity, they have to go through pseudo-Riemannian geometry, and a very popular book which I followed and still I follow is by Barnett O'Neill, Pseudo-Riemannian Geometry. Okay, so there you can see the geometric aspects, what are the prerequisites in geometry in order to learn Einstein's general theory of relativity. So Lorentzian geometry study with metrics having indefinite signature. So I think those who are from mathematics or physics, you know about quadratic forms and signature of quadratic forms. When a quadratic form is said to be positive definite, when it is semi-definite, negative definite, all those things. Now, in case of Lorentzian geometry, the space-time metrics that we deal with are indefinite in nature. As you can see, time is different from the other three space coordinates. So that is what is present in the Lorentzian geometry. And the concept of causality, that means past, future, all these things are present in Lorentzian geometry. And that is the reason this geometry plays as the backbone of Einstein's general theory of relativity. The of Einstein's field equations lies in the nice interplay between matter and geometry. Those who want to have a clear idea of general relativity and geometry, they may refer to these two archives. You can simply Google it, stating the archive, and you can get the mathematical foundations and every calculation, a lot of problems discussed. You can get all these things from general relativity and the Lorentzian geometry, the differential structures involved to learn the general relativity. So I think now we are able to understand the difference between the Newtonian and Einstein gravity. Next is the equivalence principle. This is the principle which led to the foundation of Einstein's general theory of relativity. All these details you will get in these two archives, but since you have devoted time here for my talk, I'll just give you a little say essence of this. Equivalence principle actually says that whenever that is the gravity and acceleration are same, and this revolutionary idea led Einstein to write his field equations and just uh, start his general theory of the start the journey of general relativity. Right. So this equivalence principle, everything is given in these two archives. You can refer. Now, why do we answers in order to understand Einstein general theory of relativity? Actually, what happens is that in Euclidean geometry or flat space time or Newtonian case, you can say uh, there is no aspect of time because time is absolute over there. But here, in case of curved space-time, in general relativity, space-time curvature is there, and there is notion of space and time as entities. So there, what happens if you try to learn any physical law or want to conclude some physical implications, then there might change coordinates, right? So if we change coordinates, our set of equations in one coordinate may not be remain invariant in the other coordinate system. So that is the problem encountered. So what tensors do is that by this law of general covariance, allow the invariance of the equations under any coordinate system. And ultimately, this leads to a general and unique conclusion regarding any physical phenomenon. So there lies the need of tensors. So let me repeat, tensors actually allow the invariance of the set of equations under any kind of coordinate transformation. That means if you do the calculation with tensors, then you can be very by the law of general covariance, my equations are not going to change whether I change my coordinate system according to my choice. What the mathematicians do is that suppose in some set of coordinate system, the calculation is getting tougher. So I can suitably change the system, and this under that change of coordinate system, my results will remain unaltered until and unless I don't use the tensor. So tensors play that crucial role. So these are some prerequisites in order to learn the general relativity. Like you have to master the skill over tensors and differential geometry, curvature, hypersurface, time-like vectors, null vectors, space-like vectors. So all these are given in these two archives. Those who are interested, they might go to. As I was saying that suppose there is a flat space-time. Now there are 2 points, uh, path joining these 2 points. The very obvious, it's a straight line, right? But what if the space-time is curved? What we see in general relativity. There, the short does not remain a straight line. For example, if we consider path becomes the great circles. That means the equator or the longitudinal lines, right? So there comes the geodesics in curved spacetime. So you can think of the generalization of the straight lines from Euclidean geometry to any curved geometry are the geodesics. So suppose in the spacetime manifold, a test particle want to go from one point to the other. What is the way? He has to follow the test particle has to follow the geodesic. For example, you see, this is the space-time manifold. Suppose sun is there. It is creating a dent in the space-time and there is some other planet. So the planet revolves around the sun along the geodesic line. So this is what the geometric characterization of geodesic all about. So mathematically, this differential equation represents geodesic, where you can tensors. This is the Christopher's symbol. Okay. Now this represents the curvature of the space-time. Okay. Now for flat space time, there is no curvature. So if you make this quantity zero, if you solve this differential equation, you will get a straight line. So that means geodesic, this is a very generalized differential equation representing a geodesic for any curved space time, right? So whenever we just vanish the curvature, that means we are talking about the flat space time. There, the geodesics are simply the straight lines. Okay, so this is also included in differential geometry course. Next comes some drawback. I mean, the most important drawback of Einstein gravity. So till now, we all are very well aware that Einstein's general theory of relativity is able to explain a lot of phenomena like the gravity waves, gravitational lensing effects, redshift, accelerating universe, and cosmology, everything. But this theory has a drawback. The biggest drawback are the existence of singularity. Okay, so term singularity is not such a very good term in the language of mathematics or physics. Singularity, the term itself shows that there are some problematic points in the space-time manifold where the laws of physics break down. I mean, the space-time becomes pathological. Hmm? So same thing happened in case of Einstein's field equations also. Now, under different mathematical and physical assumptions, when uh, Einstein tried to find solution of its field equations, he saw the existence of singularity. Einstein himself was very much well aware of the existence of singularity in his general theory of relativity. The first solution that I'm going to talk about is the black hole solution. Okay, so this is the black hole metric, as you can see. Now, clearly, the points r equals to 0 and r equals to 2 gm are singular points because the metric blows off at these points. All of you can just see. So these are some problematic points in the solution. Next, if you look at the cosmological solution, then here, if this at function of t is not smooth, that means not continuous, and if r square is something like 1 by kappa, then also these solutions become singular. So now we can understand that there are some problems in the theory also, which is namely the problem of singularity. So idea of the singularity. So let us try to define what a singularity is. A space-time singularity can be thought of a point in the space-time manifold where the space-time becomes pathological. So just consider the space-time manifold to be very smooth everywhere, but there is a point in the manifold where the manifold no longer remains smooth, and that point has been identified geometrically as the point, or the singular point in the manifold. Okay, so actually the curvature becomes infinite, right? And no physical laws can be meaningful or can be studied over there. But we are more interested towards drawing a formal and geometric mathematical definition of a singularity. So there comes Nobel Prize in Physics 2020. Roger Penrose bagged Nobel Prize in 2020 for his seminal singularity theorems on black hole. He proved the black hole singularity, and for the first time in literature, he put forward a formal definition of space-time singularity in terms of geodesic incompleteness. So now you know what are geodesic. Now, what is this incompleteness? This geodesic incompleteness is, let me just briefly give you the idea. It has a lot of mathematical definitions and all. Uh, Actually, geodesic incompleteness is that and the geodesics, along the geodesics, the test particles are moving. Then at a certain point, geodesic just encounter a singularity. That means a break. Okay, and there's a point of no return in case of black hole, which was proved by Roger Penrose. So in the path becomes incomplete and abruptly ends at some point in the space-time manifold. That point is referred as the focal point or conjugate point. You can see the book, or the paper of Penrose, for which he bagged the Nobel Prize. So he described the idea of space-time singularity in terms of geodesic incompleteness. And Hawking and the Stephen Hawking proved the existence of cosmological singularity via time-like geodesic incompleteness, and Roger Penrose proved the existence of black hole singularity via null geodesic incompleteness. Actually, geodesic incompleteness is the actual reason behind space-time singularity, whether it's a black hole or a cosmological singularity or what we say as the Big Bang singularity from which the universe actually started. So that depends on the type of geodesic, whether it's a null geodesic. Null geodesic we talk about in case of black holes, and time-like geodesic we talk about in case of cosmology, right? So Hawking and Penrose's singularity theorems are believed to be the greatest theoretical accomplishments of GR till date. And let me tell you, I was during my MSc days. After the Nobel Prize, I started reading a lot of topics on singularity, and I started learning a lot of geometric tools. And the pseudo Riemannian geometry book that has a lot of topological theorems also. So if you just want to study, I will give you references. But these are fascinating idea, and you will be very amazed to see how Roger Penrose proved the singularity theorems. Now, let me tell you at this point, it just goes without saying, it should not go without saying that Roychoudhury equation serves as the basic ingredient of Penrose's theorem. Professor Amal Kumar Roychoudhury, our own very scientist and physicist, his equation in general relativity proved as the main, served as the main ingredient in the proof of the singularity theorems given by Roger Penrose and Stephen Hawking. There lies the importance of Roychoudhury equation. And in this context, I would like to mention that my whole PhD thesis work is devoted to exploring Roychoudhury equation in various cosmological backgrounds. So, so from this, a very nice area of research can be understanding the meaning of singularity in different backgrounds and trying to resolve them. Otherwise, we cannot study the physics. But the singularity theorems, together with the Roychoudhury equation and focusing theorem, proves the inevitable existence of singularity in Einstein gravity. Okay, so in Einstein, classical Einstein gravity, singularity resolution doesn't make any sense because the theorem has proved that yes, Einstein gravity is singular. But what are the resolution techniques? We can quantize gravity. That means we can talk about quantum gravity, not the classical gravity, and we can see whether in the quantum regime the classical singularity can be alleviated or not. And rest is the modification of geometry. Like if we modify the gravity sector, that means if we go from Einstein gravity to some other modified theories of gravity, so is singularity still inevitable? So these are some good areas of research from this singularity topic. Quantum gravity. So the question is, can gravity be quantized? So actually, in principle, it can be quantized, but in order to find a consistent theory of quantum gravity is one of the challenges in physics. Okay, still people quantum gravity, and some of the approaches are string theory and causal dynamical triangulations. All these things are there. If you're interested, you can go through. Although I do not work much on the full quantum gravity aspect, but in some papers I have worked on the metric quantization. That is not a full description of quantum gravity. I cannot infer from there. Next, let us see about the observations. Now, cosmic microwave background radiation, CMBR, large scale structure of the universe, redshift, and expanding universe, dark matter evidence, everything suggests that at present, universe is experiencing an accelerated expansion. Now, who can be the possible candidate behind this? There must be some driving force that actually is responsible for this accelerated expansion, right? So for explaining this observation, the theoretical cosmologists are divided into two groups. One group suggests that modification of gravity is required to explain this observational phenomenon. That means in Einstein gravity. And the other group says no, the presence of dark energy is responsible for this kind of accelerated expansion. Now, in case of modified theory of gravity, you can see a plethora of gravity theories in literature. Every day you open archive in physics or any sparse high energy physics, any website, you can see that a lot of research papers in modified gravity theories are going on. So actually, the methodology to modified gravity theory is that when if you see the derivation, heuristic derivation of Einstein's field equation, it starts with an action principle. There is a term like Ricci tensor that represents the scalar curvature, right? So that is present in the Einstein gravity. But if you replace that Ricci scalar by an arbitrary holomorphic function f of r, the modified gravity formed is known as FR gravity. Similarly, so here gravity comes via curvature in the functional form of r. Next, ft gravity. T is the torsion. So here the effect of gravity comes via torsion. FQ gravity. Here the effect of gravity comes via Q, which is the non-metricity scalar. Again, in order to learn about non-metricity or non-metricity scalar, you need to have some idea of the differential geometry, affine connection, metric connection, all these things you should learn. Then you will be able to understand what is Q. But for the time being, you see that there are some non-metricity scalar present in the curvature where via which the gravity comes into effect. So that leads to FQ theory of gravity. Next comes a lot of scalar tensor theories, and recently this four-dimensional Gauss-bounded gravity theory is gaining a lot of interest. Next comes Einstein-Cartan theory, Russell gravity. Then there is fractality. So I think you know about colloids and fractals. So in case of fractal gravity, the universe has been considered as fractals. Okay, so keeping that very idea in mind, they developed the Russell gravity and the fractal gravity. Next, there are some coupled RT, QT, namely FRT, FQT theories, etc. So in this way, you can look at a lot of modified gravity theories where the the model parameters are constrained in such a way that all these theories, the cosmology actually satisfies the present era of accelerated expansion. So researchers in these fields also are very popular. Next, there are some dark energy candidates, namely the cosmological constant. Now, in Einstein field equation, can you recall I was telling the capital lambda being the cosmological constant? So it is the simplest form of dark energy you can think about. Next comes tachyon, quintessence, Chaplygin gas, K essence, phantom energy, holographic dark energy. So these are some candidates of dark energy. So if you are interested to do research in the present observational scenario, you can either take up any of the modified gravity theory and study the cosmology over there, or you can take up any dark energy candidate and study the cosmology over there. Um, Now, there are some cosmological phenomena on which you can actually do research, namely the cosmic inflation, the inflationary era. In the cosmic stage of evolution, I said the inflationary era, where the scale factor behaves exponentially. So that is an area. There are two types of inflation, cold inflation and warm inflation. There are many papers you can go through. Next, bouncing cosmological model. So this is a very interesting cosmological model. Actually, this removes the initial Big Bang singularity. How? In this case of cosmological models, it is assumed that universe either mm, first starts contracting, reaches a minimum size, but again it expands, or the reverse. The universe expands slowly, reaches a maximum volume, then again contracts. So these are the two principal classifications of matter bounce or bouncing cosmological model. Okay, so actually in this cosmological model, there is no notion of zero volume. That means I said the universe either contracts, reaches a minimum volume, but that is not zero. So the initial then again it expands. Okay, or the vice versa. Now, related to the bouncing cosmological model, the mathematicians can study a lot of mathematical properties. So I have a paper on the bouncing cosmological model. So if you are interested, you can go through. Okay, so there generally I have talked more on the mathematical aspects of bouncing cosmological model rather doing the physics, but at last I gave some physical interpretation also. Next comes the emergent universe scenario. In case of this emergent universe scenario also, the initial Big Bang singularity is avoided. So these are some non-universe you can think about. Now there is some particular nature of the scale factor in emergent universe scenario you can see. Next comes the cosmological perturbation theory. So this perturbation theory is very, very important in cosmology. This studies actually small deviations from perfectly homogeneous and isotropic universe. So in cosmological principle, we learned that universe at a very large scale is isotropic. But this perturbation theory allows us to study small deviations from the homogeneity and isotropy. And actually, it helps us to understand formation of large scale structures like galaxies, clusters, superclusters. About some compact objects. So you saw the black hole solution as a vacuum solution of the Einstein's field equation. So what is a black hole? So see, I have given you a picture. So black hole is a region of space-time. The key feature is that here the gravity is so strong, nothing, even not light can escape. Just think the um, effect of gravity is so strong there. So that is why it's a point of no return, we say. Hmm? So there are few types of black holes based on their features. Like if there is a spin, means rotation, or if there is a no spin, that is non-rotation, or if there is a charge or not, based on which we can categorize black hole as Schwarzschild black hole, which is non-rotating. It is described by the Schwarzschild metric. Next comes Card black hole. Card the characterization is it is a rotating black hole, Carr metric. Rn black hole, it is a charged black hole. And finally, the Carr-Newman black hole, it is rotating as well as charged. A black hole, so there is existence of event horizon. Actually, this event horizon is the point of no return. Next, singularity. It is a region of infinite curvature. And ergosphere. Ergosphere is present in case of only rotating black holes. It is a region outside the event horizon where there is frame dragging or space-time is being dragged. Uh, these are some theoretical properties and observational evidence behind the existence of black holes. As I said in my very first 2 to 3 slides about the Event Horizon Telescope images. Okay, the Event Horizon Telescope captured the first direct image of black hole's shadow in the center of M87 in 2019, and in 2022 it imaged the Sagittarius SGRA star black hole at the center of the Milky Way galaxy. Our galaxy is the Milky Way galaxy. So these are two observationally evident black holes. Their shadows or the images by Event Horizon Telescope has been found. Next comes the LIGO Virgo observations. Again, this is a very uh, nice discovery, and which is in favor of Einstein gravity. The first detection in 2015 of the gravity waves, and it confirmed merging black holes. Since then, dozens of black hole mergers have been detected, but these were the first ones. Next, quasi-normal modes and gray body factors. So these are also very good areas of research because these are related to gravity waves astronomy. So any people interested in gravity waves should have encountered these terms, quasi-normal modes and gray body factors. Actually, these describe perturbations in gravity waves, they behave near a compact astrophysical object. So all these are astrophysical objects, black holes, and next some of the astrophysical objects I will be talking about. So this quasi-normal modes and gray body factor to like separate that this is a black hole or this is some other compact object. So these are that is why very observationally sound, but their derivations are purely mathematical. By invoking the Schrodinger equation, it can be proved that how perturbations such as gravity waves they behave near a compact astrophysical object. Okay, so this QNMS, that means quasi-normal modes and gray body factor near a compact object, can dictate whether the compact object is a black hole or any other astrophysical object. Next compact object is neutron star. The key features are the mass is like this and radius is like this, and you can see the image. The density is comparable to an atomic nucleus. This is the image of neutron star. You can see the image of white dwarfs. Okay, it is the reminiscence of a low mass star that has exhausted its nuclear fuel. The key properties are the mass is less than 1.4 solar mass, which is popularly known as the Chandrasekhar limit. The radius is of Earth sized, and composition mostly carbon and oxygen is there. This is the pictorial representation of white dwarf. So yeah, so these are some observational evidence black holes. So first, the Event Horizon Telescope of black holes like this, M87 and Sagittarius, as I said. Next, the light observations. They detected the gravity waves and they confirmed the merging black holes. Now, also very important areas of research in the terms of observational gravity wave astronomy. The reason is that these actually allow how perturbations such as the gravity waves uh, they behave near a compact astrophysical object. That means if we can get the idea of quasi-normal modes and gray body factors near a near an unknown compact object, we might be able to identify which type of compact object is this, whether it's a black hole or some other compact objects. And the derivations of these quasi-normal modes and gray body factors are purely mathematical. Um, so if anybody is interested, they can go through these topics of observation also. Next compact object is the neutron star. The key features you can see, this is the mass, this is the radius, and the density is comparable to an atomic nucleus. This is the picture of neutron star. Next, white dwarf. White dwarf is actually the reminiscence of low mass star that has exhausted its nuclear fuel. The key properties are the mass is less than 1.4 solar mass, which is the Chandrasekhar limit. The radius is Earth-sized, and composition it is mainly composed of carbon and oxygen. This is the image of white dwarf. Now, this is a very interesting and exotic compact object, which is the wormhole. Now, what is a wormhole? Although we have got observational evidence of black hole, till now we have not got any observational evidence in favor of wormhole configuration. But it is till now a hypothetical object. Actually, what is its structure? It is a tunnel-like structure that connects two separate points in the space-time. For example, if one or in between two units, it is a passage that allows for traveling of the test particles. So suppose here one universe is Earth, it is our universe, and some other universe is there. So if wormhole configuration really exists, then traveling from one universe to other universe, that means interstellar travel, intergalactic travel, inter-universe travel is allowed. Okay. But what happens is that in case of Einstein gravity, the matter which is necessary at the throat for the existence of viable or feasible wormhole is exotic in nature, having negative energy density. So that kind of matter is not at all realistic or usual matter. So that is why that this has remained as a hypothetical object, but it has a very beautiful mathematical topology. If you want to learn about the topology of wormhole, then it is non-simply connected topology. And the traversability of the test particles from one point to the another is supported by exotic matter in Einstein gravity. But this might not be the case if we modify the gravity. That means if we have some modified gravity theories, there the matter at the throat might not be exotic. That can be normal or usual matter also that satisfies the positive energy densities and all those things. So in that case, whether the traversability is possible or not, that is also a very good area of research that many people do. So actually, these are shortcuts across the universe. Wormhole geometry or wormhole topology, wormhole physics, anything you can say. So from wormhole, we might be able to answer the whether time travel is possible. That means suppose we consider the present epoch or present universe status and we consider the early universe, the past. So if the traversability or a feasible wormhole exists, then we might be able to traverse to our past. That is what we say as the time travel, right? So from the idea of wormhole geometry and wormhole physics, might be we can be able to answer whether time travel is possible or not. Now, this type of wormhole geometry can be found, it's very interesting, can be found as a solution of Einstein's field equations. And Einstein and Rosen, they formed this kind of wormhole structures. Although the Einstein and Rosen's work, the wormhole structure that they gave was non-traversable, and so that wormhole structure is also known as Einstein-Rosen bridge. Okay, so that was non-traversable although, but later Ellis, Morris, Thorne, all they gave some beautiful traversable wormhole metrics. Now, I am almost at the end of my talk. So let me give you ideas about the current areas of research in gravity, cosmology, and astrophysics. So in generally, testing GR is one of the strongest fields, using the gravity waves, neutron stars, black holes. Next comes the modified gravity theories, as I said, FR gravity, FT gravity, some coupled theories of gravity are there, scalar tensor theories, rastral gravity, non-minimally coupled scalar tensor theory. All these things are there in case of modified gravity theories. So you can study whether singularity is still inevitable in modified theories of gravity or not, or whether matter required at the throat of the wormhole is usual or not if we study wormhole in some modified or extended theories of gravity rather than studying in Einstein gravity. Next, quantum gravity. People study about loop quantum gravity, string theory, and emergent space-time models, gravity wave astronomy, and recently the quasi-normal modes and gray body factors are very, very discussed topics of gravity wave astronomy. Next, the frame dragging effect of rotating black holes, and above all, the area where I am recently a lot of engaged and interested in is the exploring metric structure in Lorentzian manifolds. Actually, I am very much interested to extend some manifold theory so that that theory might be able to alleviate the singularity problem that persists currently in Einstein gravity. So I am exploring a lot of metric structure, whether the geodesic paths can be made complete. Although everything I am doing mathematically, I have not thought about its physical implications and all that. In any case, exploring the metric structure in Lorentzian manifolds to mitigate the effect of geodesic incompleteness is one of the very nice geometric topics related to gravity and cosmology. Next, in cosmology, the nature of dark energy, dark matter, and dark energy candidates, cosmic inflation, then large scale structures, galaxy formation, Hubble tension, primordial black holes as dark matter, then cosmic inflation in modified theories of gravity, studying warm inflation, cold inflation in various geometric backgrounds, emergent universe scenario, the bouncing cosmological model in modified gravity theories. All these are very nice areas of research in cosmology. Finally, in case of black holes and other compact objects, the event horizon imaging, that is what is capturing the shadows of different black holes and wormholes. So in this context, I would like to say that people have got the black hole shadows images of Sagittarius and M87. Now they have got observational evidence. Now what people do is that they study the theory, they study other theoretical compact objects and try to find their shadows either numerically or analytically by some various numerical or analytical techniques that I'm not going into detail. Then what do they do? Compare their shadow with the so-called that has been observed in M87 or Sagittarius. They compare and contrast that under what constraints our model can be refined or constrained so that the shadows matches with those observationally found. So these are some very good areas of research in theoretical astrophysics and cosmology. Then supermassive black hole growth, neutron star, exotic compact objects, black hole information, tidal disruption events, and finally, as I said, shadows of wormholes and their observational signatures in terms of gravity wave astronomy, namely the quasi-normal modes and gray body factors. Now, I think these days we all are very much inclined towards artificial intelligence and machine learning. So, although I have not yet done work on these fields linking cosmology and astrophysics, but I have seen many papers recently who are using this artificial intelligence and machine learning in cosmology and astrophysics. Basically, they are doing for galaxy classification. Now, using astrometry, exoplanets can be found by measuring tiny changes in the star's position. Interstellar tracking can be done using machine learning algorithms. Artificial intelligence help us to distinguish the from the shadow. So, given a shadow of a compact object, artificial intelligence will tell us whether it's a shadow of a black hole or that of a wormhole using some lensing and photon trajectory techniques. Machine learning can also classify the quasi-normal modes to detect deviations from general relativity predictions. Machine also analyze the CMB data and galaxy distributions to infer dark matter distribution. That means how dark matter is distributed in the universe. That can be analyzed using machine learning algorithms. AI is used in simulations of large scale structures to model the effects of dark energy on cosmic expansion. So, these are some areas on which I have found a lot of papers in literature recently coming up, which I have shown. So, thought to share with you all since most of us are very much inclined towards artificial intelligence and machine learning these days. So, these can be some possible areas of research open to you. Finally, I would like to say that the universe is an endless frontier of discovery, right? So, start learning GR and the cosmology. I hope you will be able to get a lot of problems to work with. And I can assure you that finding solution of one problem will open a lot of problems to you to find solutions in future also. What I have like felt in my small years of research work. Regarding the books, what I can say, in general relativity, you can go through books by R.M. Wald. That is a very good book. A first course in general relativity by Bernard F. Shoes. That is also a very good book. So these two books will suffice your understanding of general relativity, and the two archives that I showed in my slide. Next, in cosmology, you can study A Brief History of Time by Stephen Hawking. This is a very, very good book, and I am really a fan of this book, you can say. General Relativity and Cosmology by Ronald J. Adler. So that is also a very good book, but the book by Stephen Hawking is my favorite. Now, from theoretical astrophysics, this man, T. Padmanabhan, he has written a very, very, even you can refer to his papers in order to have a very clear idea of the topics. So, by T. Padmanabhan, you can see the book of a theoretical astrophysics. So, these are few books along with the archives you can have. And as I said, you can also note it down the pseudo Riemannian geometry by Barnett O'Neill. So, these books, I think, will serve as a very good books for the beginners to study in this field. And in literature, there are a lot of papers available. Anytime you can access those papers. Um,
First of all, I'm wishing you a very happy Women's Day, ma'am. And it was an awesome
yes,
webinar presented on a very
thank you.
special day by a very dignified personality like you. And so the Women's Day actually brings us to the celebration. Thanks to Shubhankar and Agrirath for bringing one of my favorite topics, general theory of relativity. You actually covered everything. I mean to say, starting from Big Bang up to the book suggestions. I have few questions for you. First of all, I was studying and making some videos, as you know, on what is called the Einstein-Hilbert action.
Yes,
Now, what I found, maybe I am wrong, please do correct, just to let other people also know that Einstein-Hilbert action is something which is based on the action principle, the principle of least action. Now,
exactly so.
so what I found is that instead of using tensors or partial differential equations, which is the cornerstone of Einstein field equation, Einstein Hilbert action is basically based on the action principle, which actually is a more natural way of telling how a system evolves from one point to another. And also writing those equation in one single line brings us that the mathematical complexities are not so difficult, although it
Exactly.
involves Ricci scalar,
Which is
the
scalar.
yeah
Square
the
root of
four,
minus g,
square
d4x, the
root of
volume
minus
element.
d,
Yeah.
etc. So if you can just tell us a little bit on the, because I found, although conventionally in universities we all study Einstein equation, Ricci scalar, Ricci tensor, Riemann curvature tensor, etc. But I found that Einstein-Hilbert action also is very important because it shows how the evolution of a system naturally happens and reducing the partial differential equations into a single scalar or a action principle using the Lagrangian. So if you can just throw some light that how and why Einstein-Hilbert action is important in learning Einstein field equation or general relativity.
Yes, absolutely. Whatever you said, that is what I also said. That the field equations, actually, the origin of field equations started from this action principle or principle of least action, what we see as the Einstein-Hilbert action. Okay, so if you see that action integral, from there only encodes the information of curvature or geometry via the Ricci scalar, right? So ultimately, taking the metric variation of that action principle, we can get the field equations very easily, and that as a result serves as the cornerstone. Now, I also gave you two archives to study. There you can see the heuristic derivation of the Einstein's field equations via that Einstein-Hilbert action. That is why for the beginners I suggested the two archives, because I also learned using those two archives. Actually, those two archives are written by my PhD advisor, Professor Shubhina Chakraborty. So he, what he taught in our class, we jotted down everything, and that we wrote in the form of archive. So actually, everything just follows from the metric variation of the action principle, and the integrand encodes the geometry and physics linked with it.
Thank you. My next question is that, as you have rightly told, that the left-hand side of the Einstein field equation actually helps us to measure the curvature, and at right-hand side is the matter content. Now,
Matter,
yeah.
exactly.
So I often fall in love with this beautiful equation because how beautifully it encodes everything regarding nature. Now, what I also found is that this equation, when it is studied in other way, it is something like a father and a child. A child will always carry the resemblance like the eyes and nose of a father, the characters, etc. Now, I also came to know when we are studying, it is general, that the Poisson equation actually under weak field approximation
Weak field approximation, yes.
reduces to Einstein field equation, and from Einstein field equation again you can go to Poisson equation. That shows the genius of both Einstein and
As well
Newton.
as
That how,
Newton.
yeah,
Exactly.
if you can just tell that this reducing factor, how it is important and how beautifully it is done, if you can just throw some light.
That's a very nice question. That's a very nice question. Actually, the um, like application of a theory or its well acceptedness lies in the fact that this general theory, under particular circumstances, should be able to describe the particular cases. Like what he said, that if we start with the Einstein's field equations, then if you assume the weak field approximation, what is this? Now you consider the effect of gravity to be very weak field, weak. Yes, you will be able to understand the time component of the Einstein field equations actually lead to the Poisson equation, which is a partial differential equation in the Newtonian mechanics. We are well aware of this Poisson equation. So this correspondence can be drawn. Actually, assuming the weak field approximation, the zero component or the time component of the Einstein's field equation reduces to the Poisson equation, that is actually very relevant in Newtonian mechanics. So the weak field approximation of Einstein gravity is the Newtonian gravity, and there lies the generalization of the Einstein gravity and how, as a particular case, the Newtonian gravity can be recovered. So that's a very good question that he raised.
Yeah, thank you. I also went through your profile. You have worked a lot into Amal Kumar Roychoudhury's the Roychoudhury equation, which I think is one of my favorite topics also. I've already made one video on explaining AKR, which is highly a technical field. And also to know all the viewers that in that video, I have actually taken up a lot of examples how Roger Penrose and Stephen Hawking in their many researches have cited and used Roychoudhury equation. Without that, that is not
Chaudhury's
possible.
work. Yes,
Yeah.
yes.
Now,
Hmm, hmm,
what
hmm.
I would like to know, I would rather request if you can explain that what I found that AKR argued that by simply
Hmm.
avoiding the homogeneity and isotropy, which
Mm.
brings in shear would not help. If we could include
Yes.
rotation, then hopefully we
Rotation.
could avoid singularity.
I think.
But it was
Yes, yes.
when I went to Professor, I talked also to Professor Shayan Kaur of IIT, and he told me
Mm.
that Roychoudhury equation is not only for geodesics, but it can be taken to any part of
Any
physics.
card. Yes,
Yeah.
yes, yes.
So if you can just tell us, ma'am, that how Raychaudhuri equation is so important and generalized in other areas
Mm.
of physics also.
Yes. My whole thesis work was a homage to Professor Amar Kumar Roy Choudhury. Now, yes, he was absolutely right. Roy Choudhury derived his set of equations not keeping gravity at the outset. Whenever there is effect of gravity, but Professor Amar Kumar derived his equations for any general.
Ma'am, if you can please put your mic up, then we won't lose that. Yeah.
Yes, yes. So, yeah, as Professor Shankar rightly said, the Roy-Choudhury equation is a very generalized equation. It can be reduced to the geodesic equation, but it is true for any curves. But what was your question? That how does it? Sorry, please,
How
can you repeat?
why general Raychaudhuri equation is so very generic, applicable to any other areas of physics like liquid
Yes,
or any liquid fire?
yes. So, the answer is, if you see the derivation of the Roy-Choudhury equation, you will see that the notion of vector field and integral curves are there. Now, wherever in which field, even in fluid mechanics, physics, mathematics, wherever you will find a vector field, you can apply the analogous Roy-Choudhury equation over there. So that is why the system is the actually the derivation of Roy-Choudhury equation is nothing but the covariant derivative of vector field. And specifically these are geodesics cosmology. But Roy-Choudhury equation is a very general equation. Its geodesic version is used general relativity in the proof of Hawking and Penrose. Since the context is gravity, otherwise it is true for any curves. So what are integral curves? Vector field. So in any area of physics and mathematics, wherever you can find a vector field, you can find an analogous Roy-Choudhury equation. So this is the limit of Roy-Choudhury equation. It's not restricted to only gravity and cosmology.
My last question, because I think the other viewers should also be given a chance to ask question, is that I what I found in case of students also while teaching GR is that the concept of differential geometry is very essential, because
Very essential.
general relativity is more about geometry less than more geometry, less physics. I mean to say physics is
Exactly.
there, but it is more of a geometry. So
Geometry.
yeah, in case what I would request to ask you is that we have already cited various good books in differential geometry. I want to know, ma'am, that is learning topology as a
Mm.
mathematical subject, topology, is it important in case of general relativity, or just learning differential geometry is okay for GR?
Yes. In the book Pseudo-Riemannian Geometry by Barnett O'Neill. If you want, I can share you the PDF of that book. Yes, the basic idea of topological structures, the basic ideas of topological structures uh, is very necessary. Now, there are some notions in topology which was actually used by Roger Penrose in the proof of the singularity theorems. So, if you genuinely want to learn the essence of the singularity theorems, you should not every all the idea you topological idea of manifold. Like manifolds are what? These are topological spaces that mimic the Euclidean space in a local neighborhood, right? So manifolds are topological spaces. And in the proof of the seminal singularity theorems by Penrose and Hawking, you can see some terminologies are used, like the achronal set, Cauchy surface, hmm, then causal diamond. So these are some theoretic and topological notions. So until and unless you have the idea of these things, you might not be able to actually get the true essence of the singularity theorem. So from that point of view, the knowledge in topology is required, and for that, that book can be a very good guidance because I learned from that book. It's a very good book.
Okay, so when you talk that basically manifold is any surface where you zoom it at some places, it would resemble of a locally
Semi-Euclidean.
Euclidean space.
Yeah,
Then we,
locally Euclidean. Yes.
so in that case, we understand that Einstein field equation is also applicable, particularly to a certain region in space because it is local.
Mm.
Will it be wrong to say that Einstein-Hilbert action, quantum gravity, gives us at least a theoretical chance to extend Einstein general relativity from local field to a much more generalized global field?
That can be thought of. Yes, that is a very insightful thought. I can comment about that. Yes, why not? Actually, it talks about. Mm.
Thank you. And my last point, which I would like to tell you, is that it is has been a wonderful, session for a very technical subject. And one last thing is that apart from the books, definitely Walt's book, Bernard Schutz's book is good. I personally have felt for absolute beginners who has got a basic knowledge of calculus and special relativity, there is a wonderful book which is called Sean Carroll's Space-Time Geometry.
Carol. Space-time
Yes,
geometry. Yes, yes.
that is
That
also
is
a
that is also, yeah.
very good
That
book.
we studied during my third year of BSc. Yes, that is also you can take note of, as you said.
Yes, and
That
that is
book is
widely
also great.
available as a PDF file on
File
internet
also.
also. And also, I would recommend you can go for Leonard Susskind's Stanford lectures on general relativity. It is just awesome. I mean to
Yeah.
say, he has got a series of lectures in 3, 4 semesters. Now he is almost close to 92 years. Recently, there was an interview on Professor Leonard Susskind. So, general relativities lectures, Thanu Padmanabhan, as well as Leonard Susskind's
Okay.
Stanford lectures are absolutely. And
Hmm.
Barry O'Neill, I have personally read it. It is on pseudo Riemannian geometry as well as
Okay.
differential geometry.
Yes,
Also,
yes.
I think this is
Yeah, that means learning whole theory from the point of view of geometry.
from the
So
point of
for
view of
that
geometry.
that book is very good. Yeah.
Ma'am, thank you for this presentation. I am Shashwat Tripathi, student of Ramakrishna Mission Vivekananda Centenary College, Department of Physics. I have a question for you. That
Yeah.
what is the basic difference between general theory of relativity and special theory of relativity?
Yes, that's a very basic question. So actually, Einstein developed these two theories. What he did in special relativity theory is that he considered all inertial frames. That means uh, non-accelerated frame of references. But in case of general theory of relativity, he incorporated acceleration. So the frames of references in general theory of relativity are all non-inertial, while it is inertial in case of special theory of relativity. This is a very key difference between these two theories.
Ma'am, one last question that just came in my mind that when we are talking of time travel, you were talking of wormhole. Theoretically, there is something also very fascinating which is called Gödel's rotating universe, where you can actually. So, is that basically a theoretical and a mathematical
Yes.
perspective that we can?
Only a mathematical artifact, no such physical implications has been drawn. Because mathematically we can make such structures, but whether that is physically viable, that is a big question. Like as I said, na, in case of wormhole, so in Einstein gravity, the matter at the throat that is assisting the traversability in between two universe or distant regions of the same space time has to be exotic matter. That means it has some negative energy density. Now tell me who realistically will give me that kind of matter. So if that kind of matter can be harnessed, Gödel's theory and also this time travel would be possible someday.
When you're talking about ergosphere also, I read one of the papers of Roger Penrose where he theoretically told that we can harness energy from that ergosphere. As,
Ergosphere, yes, yes, and that is why this energy which we get that is reflected in the black hole shadows, the shadows that were captured in Event Horizon Telescope, the effect of ergosphere in the shadows were not perfectly circular as what it was found. So there you can observational effect also you can see papers on EHT, Event Horizon Telescope. You will get insight about this ergosphere and all those things. Even charged wormholes also create shadows. So charge, rotation, everything, these spin or rotation, what I said, size of the black hole, that lead to formation of different shadows.
One question it keeps me busy, and I always ask speakers is that Hawking's contribution, as you told that Penrose contribution
Mhm,
was a cosmological singularity. Now, Stephen
mm,
Hawking's contribution, as far as my limited knowledge goes, is that at one point of time he influenced something. He told something which is called a Hawking radiation, a totally different concept that black
mhm,
holes do not absorb; they emit. So, what I wanted to understand from you, ma'am, is that
mm.
did Stephen Hawking use the mathematics of quantum mechanics and general theory of relativity together to get a kind of a quantum gravity? Was that
Yes,
his aim?
yes. Yes, it was his aim. Actually, they all were very aware of that singularity presence in the classical regime. So, quantum mechanically, they were trying various tools so that they can alleviate this singularity that persists at the classical level. Okay, so as such, there is no direct link with the Hawking temperature or Hawking radiation with the Hawking singularity theorem. Both of them are distinct topics, but yes, the motivation was from the quantum mechanical background only. And the singularity theorem given by Roger Penrose is in the context of black hole. He showed null geodesic incompleteness. Because in black holes, we talk about photon trajectories or null geodesics. But in cosmological singularity or Big Bang singularity, the theorem was proposed by Stephen Hawking. But he was not alive then. Penrose got the Nobel Prize in 2020. But Hawking and Penrose, there is a joint paper on space-time singularity, including both black hole as well as the cosmological singularity. So Hawking talked about the time-like geodesic incompleteness as the key reason behind the cosmological singularity. So these are all very